All right, we're going to go ahead and get started. We'd like to thank everybody for attending today's webinar titled What's in Your Concrete Specification and What Does It Mean? It's being presented by the Illinois Ready Mix Concrete Association. My name is Theron Tobalski. I'm the Assistant Executive Director. Part of my role is interacting with the engineering community, working with them to bring them up to speed on different concrete technologies, different types of specifications, and it's kind of why we're here today. So we look forward. I think this is going to be a really interesting webinar for the engineering community. Next slide, Scott. First, we'd like to cover our antitrust statement. This webinar is being held in accordance to the IRMCA antitrust policy. It's listed on the webinars tab for every one of these webinars. If you feel there's something wrong or we're breaking antitrust rules, we ask you to just exit the webinar, but we are following those rules in our policy. This webinar is being recorded, as all webinars are. They'll be posted on the IRMCA website at www.irmca.org. Next slide. On that webinar page, we'll see a list of sponsors. Today, here's a list of the sponsors for today's webinar. When you go to the website, some of the sponsors have listed different links to different information on the products and services that they have to offer. It's a good place to learn a little bit more about the different technologies you've been hearing about in our webinars. Next slide. With that, I'd like to introduce today, we have two speakers. First is Scott Kelly. He's Ozinga Director of Technical Services. And we also have Gary Hall, Pre-Material Technical Services. And with that, I'll turn it over to Scott.
Thank you, everybody, for being here with us today. I'd like to cover an overview of what's, as Darren mentioned, what's in your specification, what does it mean? A lot of high-level topics drilled down into a little bit more detail. We feel free to reach out to IRMCA or list your questions in the Q&A box, which we will gather throughout the presentation and have a Q&A session at the end, or follow up with you later as necessary. So I'd like to first talk about the evolution of the specification, right? This graphic is kind of meant to illustrate how specifications have evolved and been handed down for generations. Portions of those specifications are updated by adding newer current standards and new technologies, admixtures, fibers, those sorts of things. But realistically, how much has been cut and pasted and still remains relevant within your specification? Are there portions of the specification that contain withdrawn, outdated, or obsolete standards that should be updated? Are there standards that are not fully understood or not enforced on a project? And what impact is that having on the life of the pavement or structure that your firm or your firm's name is on? So I've listed some standards here and specifications to show some current publications as an example. Obviously, when a project is bid, there could be some older standards listed there based on when the project was designed, but here was just a couple of lists, a couple of items of some really current standards to be aware of and what their publication dates are. They're constantly being updated, withdrawn, replaced, not replaced, reorganized, which I'll talk about a little bit more here in the next couple of slides. So is your specification current? We often see outdated or withdrawn standards within a specification. We see some references to codes and standards that have been radically changed. A good example is both ACI 318, which was reorganized and published in 2019, and ACI 301, which was reorganized and published in 2020. These have undergone a total reorganization. They appear to be completely different. Whether that's good or bad, my understanding is they were reorganized to kind of follow the design and construction process. It takes a little getting used to, but if there are references within your specification to specific chapters or sections of 301 or 318, It's possible that they've been relocated or updated. So agencies should continually update their specification as these new publications come out, and be aware of those code changes as they come about. We also often see specification language related to guides and practices. Good examples are ACI 305R, 306R, and we see those as specified items within a specification. And that's not really what they were intended to do. Language within them are okay. Taking examples, practices out of those guides and incorporating them into your specification are okay. Another relevant example is referring to the PCA design and control of concrete mixtures as part of a specification requirement. We'll often see that kind of language within a specification, follow the PCA design and control of concrete mixtures. But the PCA design and control, although is a vast document and extremely informative, it's not intended to be a specification. So if you're asking a producer to follow a guide for design and control of concrete and construction, make sure that there's specific language cited from those within your concrete or specification, something that's specific that you're looking to pull out of there to put in your specification. We also see a lot of ASTM standards listed as part of a master spec, but in reality, some of these are overlooked as part of the acceptance process, and that may delay projects and add additional cost. An example of that is a temperature-controlled curing box, something that simple. We sometimes see low breaks on our projects, and this definitely will result in delays to move to the next phase of construction, while either coring or some other destructive or non-destructive testing is being performed to determine the in situ strength of the concrete. More often than not, if we look at how the cylinders were stored, stored, and handled on the project, we can trace it back to that. And that's really an unfortunate circumstance when the money is involved in job site delays in the investigation. Gary Hall is going to have some more information on that later, which I think is going to be very informative for everybody. Some other things is that we see are redundancies within a specification, pre-qualification requirements that could be satisfied by allowing existing results from agencies such as IDOT. A big example there is ASR. IDOT has really done a lot of testing on aggregates for ASR, both 1260, ASTM C1260 and ASTM C1293. They also have an ASR mitigation program in place. So it's worth considering that maybe some of those requirements or some of that testing could be utilized to satisfy the ASR requirements within your specification. Some of the codes and standards, again, that we see that some of the really good ones that we see that aren't enforced are concrete field curing boxes. Again, testing for density of concrete. We see that a lot on lightweight, structural lightweight projects, where that is obviously a very big factor relating to what we think should be acceptance of the concrete, but more often than not, there's not a scale on the project. And then of course, concrete curing and protection in hot and cold weather. And that is more than just the cylinders, that's the structure of the pavements as well. So I'd like to talk about prescriptive, performance, and hybrid specifications. Some examples of a prescriptive specification are to prescribe minimum cement or cementitious contents, maximum water to cementitious ratios, limits on slump, or prescribed aggregate ratios or minimum aggregate contents. And to paraphrase from the preparation construction specifications for civil projects, a committee on specifications of the Construction Institute of the American Society of Civil Engineers, prescriptive specifications are like a recipe for completing a project. right? It's the cake, and you're telling us exactly how to make it. That basically limits the outcome, right? And so it prescribes exactly how to produce the concrete and details of the construction procedures, the workmanship required, and several other details as well. Typically, there's obviously an intent for a desired end result, but that result is typically not precisely defined because of the prescriptive nature. And because they're not specifically designed except for defined, except for air, slump, and strength, the designer may not actually achieve the desired results. And potentially, this could result in placement of concrete mixtures that adversely affect constructability and even durability of the pavement or structure. These undesirable risks associated with the prescriptive specification include increased risk of shrinkage and curling, increased crack risk, decreased workability and placement issues, which is a really big one, decrease in durability, and of course, increased costs. Increased costs are exactly tied to each one of these risks because obviously any of those risks that finally occur or do occur on your project are going to result in remediation, delayed schedules, potentially removal and replacement, or premature failures of the pavement or the structure. This is taken basically out of the NRMCA's specification and practice series, and it's a basic guide related to strength and water cementitious ratios. We often see unusual specifications. An example is to specify a 3,000 PSI concrete mixture with a 0.4 maximum water to cementitious ratio as an example. And what this does, this basically is going to require a producer to supply a 5,000 PSI mixture, which could cause placeability issues, obviously have cost implications. And we're sure that there's more than likely a driving factor here, such as reducing permeability is one example. But our question would be to you is why not specify a limit on permeability? It's likely that approach would provide a much more cost-effective mixture and ultimately would provide a known result instead of an assumed outcome. It should be noted in this chart that lightweight structural concrete is not included, and lightweight structural concrete should not have limits on water to cement ratios, and that's defined in ACI 301 as well. This is taken right out of ACI 301. And its limitations on cement replacement with supplementary cementitious materials. ACI 301 only limits replacement percentages of Portland cement for class F3 exposure, however. We very often see limits on SCM replacements in other exposure classes, including those that are not exposed to moisture in service or freeze thaw or de-icing salts. And I think that the community is really missing out on some innovation here, and other great benefits like reducing the global warming potential of your structure. And so if there's an opportunity for you to include increased levels of SCMs, blended cements, and other alternative cementitious materials, especially where 56 days or even longer ages can be considered in your construction schedule, I think that can be advantageous to providing a higher performing concrete, which will lower the global warming potential of the structure or pavement. And more than likely, as most studies show, increase the life cycle of that pavement or structure as well. So performance specifications, as described in the same article by the American Society of Civil Engineers, describes the end product that is desired, right? So this is a prescription of the end result rather than of the recipe itself. It doesn't describe how to achieve the result, and the contractor most often can choose those products, equipment, and construction procedures from various available alternatives. The ability for a contractor to choose those materials or practices and alternatives for construction for the specific needs of that project can lead to innovation, improved quality, and optimized products and construction procedures. The responsibility of the designer in a performance specification is to adequately define the end result to ensure that the intended outcome is achieved. And that's one of the things that we here at IRMCA are definitely excited to speak with engineers about, is what does that look like to develop a performance specification, and what are those test results that will give you the confidence to achieve the end result that you're looking for. Clear testing and inspection criteria should always be defined, and the contractor now bears the responsibility to research those different alternatives and develop the needed data and propose the products and processes to the designer needed to achieve that desired outcome. It does sometimes and often require a longer lead time during the bidding and submittal process, but the improved life cycle of the pavement or structure and the cost savings, the reduced environmental impact, all can have a much more significant impact than what that longer lead time is. And with technology the way that it's going right now, chances are that a lot of producers have some of this performance data in their library already. New technologies like Portland limestone cements, blended fly ashes, and other alternative cementitious materials, CO2 mineralization, and certain admixtures like strength enhancers, permeability reducing admixtures, viscosity or rheology modifying admixtures, moisture vapor reducers, waterproofers. Those are just a few examples. Obviously, SRA's been around for a long time, corrosion inhibitors, those kinds of things. But those are some examples of materials that can be utilized in a performance specification to increase that life cycle and lower the global warming potential on your project. So a great way really to incorporate a performance option into your specification is to create a hybrid. So what a hybrid means is you can already leave in your specification what's there, right? What's tried and true, what you've depended on for years to complete your project in a safe and effective manner. But you can allow a performance option, right? And that's a great way to start to allow innovation, but still provide that roadmap that meets those basic design requirements that you've relied on and probably have experience with on previous projects. So I'm going to turn this over to Gary for the next couple of slides. He's going to get into some more detail about some other technologies and some job site conditions as well. Gary?
Thanks, Scott, and thank everyone else for attending. And expanding upon Scott's references to the performance of concrete admixtures, although they are low in volume and weight as far as their composition and the mix design, they do contribute a great deal to the performance of not only standard concrete, but high performance concrete as well. Currently on the screen, you see the typical workhorse admixtures that fall under ASTM C494. These are all commonly specified in concrete specs with your type A, normal water reducing, retarding admixtures, accelerating, high range water reducers for both slump increase, normal water reduction, and then control of set time, either accelerating it or reducing it to maintain normal set time under varying conditions, or to increase or decrease it under extraordinary conditions for specific type of placements. Beyond the workhorse, we have what's called type S, or specific performance admixtures that play a real key role in producing high performance concrete under certain conditions with high life cycle expectations, unusual placement conditions, et cetera. And then the C260 air entrainment obviously is the spec that applies to providing an air void system in the concrete for air entrained concrete. Next slide, Scott. So here we have a list of the type S admixtures for higher end or unusual performance conditions, which include shrinkage reducers, corrosion inhibitors, viscosity or rheology enhancing. Typically, those are used for high flow, high slump concrete. Perhaps you have congested rebar placement, and we have to get the concrete to go through there. Anti-washout, which is used for underwater concrete placement, typically on Army Corps of Engineer lock jobs or other underwater placements. Permeability reducing admixtures, moisture vapor reducing admixtures, typically for interior slabs, where there's a concern for the inherent moisture in the concrete rising and causing perhaps a debonding of a flooring toppings as well. We also have waterproofing admixtures for different structural concretes that may be in water retention structures, and we're trying to prevent water under typical pressure conditions from entering the concrete. Integral sealing, that's pretty common with driveways. Perhaps you have contractors that don't want to do the extra step of going back to a project and properly sealing the concrete. So we can save them the trouble of doing that by incorporating integral sealing. Of course, carbon mineralization, we know is a popular theme now in terms of global warming reduction. And carbon is CO2 is basically injected into the concrete at the plant and causes carbon mitigation over time. And then there's strength enhancing admixtures, which not to be confused with accelerating admixtures. These work on a different phase of the cement, and after the concrete's in a hardened state, it works on the cement phases to accelerate strength. Good example of that would be you have a runway, a live runway that has to be shut down temporarily, mass transit platforms, or pavements even, that you have to get temporary closures, and there could be potential for big fines if it's not reopened in a timely fashion. So that gets us a lot of strength really fast. And then of course there's slump retention admixtures, which are really not a retarder, and they're not a high range water reducer. Basically, they cause the concrete to hold slump over an extended period of time and really don't have an impact on the initial or final set of the concrete. Next slide, Scott. And then of course we have ASTM 1116, which discusses the use of fiber reinforcement. And different examples of fibers are monofilament, and typically that may be used in residential concrete where the aesthetics may be important. They do provide plastic shrinkage crack mitigation, not prevention, but mitigation. Fibrillated fibers perform the same function as well. Then when we start getting into higher performance concrete, we take a look at macrosynthetic and steel fibers, which can provide, excuse me, an alternate for welded wire fabric and temperature steel replacement. And they can also be used in high performance floors where you want to extend columns or control joints in the flooring, which could be important for warehouses. And you could also use those to optimize pavement designs as well. Next slide. Then we move on to, once we establish mixed proportions, whether standard or performance, the next phase would be job acceptance of the concrete. So obviously we have to verify the mix on the delivery ticket to make sure the right product is actually showing up on the job. That's common sense. And then we do the basic plastic testing on the job site, which includes proper sampling. And sampling typically takes place in the middle 2/3 of the batch. There is a provision where if you're just checking for initial slump and air content, you're allowed to take that from the first quarter yard of the concrete. However, if you are composing cylinder samples, the sample should come from the middle of the concrete batch. We also test for slump or flow, which is a measure of the workability of the concrete. That's typically done to the nearest quarter inch, temperature to the nearest degree, and then we move on to air content for air entrained concrete, which is done either by the pressure method in the case of normal concrete, or the volumetric method in the case of lightweight concrete. We also have unit weight testing, where a unit weight scale is provided at the plant or the job site. And the unit weight scale, we could actually use that in conjunction with the air pressure method bucket, because it is a specific or known volume that's calibrated. So we use that for density measurements and also yield measurements as well. And then ASTM C31, that covers the casting and storage of cylinders and beams on the job site. Next slide. And on the screen is an example of the typical concrete testing equipment for both plant and field testing of concrete, with the slump cone on your left. Then we move on, going clockwise, to the pressure method for air content, the volumetric method used for lightweight, thermometers, which should be accurate to 1 degree, and the unit weight scale accurate to 1/10 of a pound. And of course, a water bucket. Next slide. So as far as the job site, we do have specs and codes that cover the casting and protection of concrete cylinders, because as we know on the job, concrete strength is the major mode of acceptance for the quality of the concrete. So we want to take extra care to make sure that the casting and protection of the cylinders is done according to the codes and specs. And cylinders seem to be a common problem in terms of low breaks that could be easily resolved. And then ACI states that contractors must provide space and electricity for the curing boxes, which is the preferred method of storing cylinders on a job site for initial curing. And it should be a spot that's obviously out of the way of construction activities. And then we want to make sure that suitable ambient conditions exist for protection as well. for temperature, sunlight, and wind. Obviously ground level where your box is. And then once the cylinders are cured on the job site, we have to transport them to the lab within 48 hours. We also look for distribution lists for as a ready mix producer and all parties on the job site. Next slide. On the screen is an example of acceptable cylinder storage on the job site. Curing box. On the left, you also see a box with a mini max thermometer to control the initial curing of the cylinder temperature, which should be 60 to 80 degrees. On the right-hand side, the initial curing is also taking place in water, which is acceptable, as long as the temperature conditions are still maintained at 60 to 80 degrees. Next slide. On this slide is an example of what we don't want with cylinders on the job site. On the left, obviously, you see cylinders that aren't covered. They're most likely in direct sunlight. Center photo shows cylinders that are stored in not so good ambient conditions. They can possibly freeze, and both frozen cylinders and frozen concrete, your strength could be impacted by as much as 50% with no chance for recovery. On the right-hand slide is a bad example of transport. The cylinders are, laid out in the open like that. It could be cold out. They're not under the right conditions for transport. They could get damaged if they move around. And of course, those cylinders, if they're representative of the concrete in place or not representative, that could lead to investigations and delays as to why the cylinders failed. And you'd have to verify the strength of the concrete in place. Next slide. And then we move on to low cylinder strengths and possible causes and corrections for that. First of all, we have to verify that the results are in fact correct. And we also want to take a look at the data that is recorded on the cylinder report, because that could lead to clues as to why we may have failing results. So we want to take a look at both concrete and ambient conditions, as well as the air content of the concrete. Obviously, if a spec on an air is 5 to 7% on for a mix design, and our recorded air content is 9%, then naturally that's going to lead to low strengths. We take a look at the type of fracture when the cylinder is broken at the lab. The fracture types are typically listed on the cylinder reports, which could lead to clues as to possibly how the cylinder was cast, or maybe conditions in the laboratory that may have led to different types of failures. And then, of course, improper casting, handling, curing can all lead to conditions that might result in cylinders that aren't representative. So we have to make sure we adhere to the ACI and ASTM standards provided. Thing is, the testing involved in terms of checking plastic, concrete, and casting of cylinders, they're relatively simple tests to perform, but we have to make sure that we follow the procedure because the fact that they are simple sometimes could lead to maybe a little oversight or assumptions that everything is taking place correctly. In the event that we do have low cylinder breaks, we have a number of standards that are provided or recommendations in terms of investigating low cylinder results. First of all, we have to take a look at the statistical analysis due to low cylinder breaks actually result in low average cylinders, because we determined that by an average of running average of 3 breaks. And if the cylinders fall within that, then we can assess that the strength is correct. Other in-place strengths, if we've exhausted that, we can do penetration resistance or coring to determine if the in situ strength of the concrete is in fact okay. Then we could resort to petrography as well to look for root causes of concrete failures as well. Next slide. And part of the performance of concrete is that we have to perform under varying conditions. So we have guides and specs for placement in both hot weather and cold weather. So some of the hot weather concerns include, from a producer side, cooling the concrete to acceptable temperature limits. And then we have to also address the controllable job site conditions in which the guide, the ACI guides have recommendations, and those include wetting the subgrade, wind blocks. We do have admixtures for controlling the set of the concrete in summertime. And also, of course, we have to make sure that the labor force is adequate for placement. And on the flip side, you have concrete cold weather conditions. As a producer, we have to make sure that we heat our materials and water to produce adequate concrete temperature. And again, addressing controllable job site conditions as far as managing the site environment. So we have to maintain and create an environment suitable for placement. This would include preheating possibly of the ground. We don't want to pour on frozen ground. Then including the use of wind blocks, tarps, etc. And then again, we have admixtures to assist with maintaining set times under those conditions as well. And a recurring theme too is in addition to protecting the concrete, we have to protect the cylinders that represent the concrete as well. Next slide. So from a producer standpoint, to meet our end of the obligation during hot weather, we could simply sprinkle or mist the aggregate stockpiles to create evaporative cooling of the concrete materials. And then we could also incorporate the use of chilled water with the chilled water system, ice, throwing bags of ice in the concrete and replacing a portion of the batch water with the ice. And that's counted in the water cement ratio calculations. A more extreme example would be a liquid nitrogen system. That typically would be used for placing massive structures such as piers and mass foundations, etc. We also have the use of retarding and hydration stabilizing admixture to control setting time. Another option would be nighttime placement in hot weather as well. Next slide. So here's an example of the extreme control of concrete and warm weather conditions. On the left is a wand nitrogen system where a wand of nitrogen is injected into the concrete mixer after the concrete is loaded. And then it's in there for a specified period of time to achieve the desired amount of cooling based on calculations. A better option that's more common these days is incorporating the use of a nitrogen system that's tied in with the batch plant, which happens during the loading process. So it doesn't result in extraordinary delays in the loading process. And we use that to reduce the concrete temperature within spec. And it's a much faster, much safer process. Next slide. Production of concrete in cold weather incorporates the use of hot water. We can even use steam pads for sand, possibly even steam in the aggregate silos like we may have in some locations. And then the use of accelerating admixtures to control set time as well. Next slide. And here we have examples of hot water and steam setup at a ready mix plant with the hot water system on the left and then the steam pad on the right. And we typically use those with the automated blending systems that detect the temperature of both the hot water and the steamed aggregate, so that we can blend in the proper amount of water in order to produce the desired concrete temperature. And that is it for the specs regarding temperature control. I turn it back to Scott.
Thank you, Gary. I appreciate it. Before we move into some discussion on cements and supplementary cementitious materials. And so the question is does your spec allow all cements that are available and both in ACI 301 and also some of those that are new technologies emerging in the market? Some examples, and these are all of these three cements appear in ACI 301. And that's ASTM C150. That's a prescriptive nature. Definitely all the chemical composition is prescribed within limits. ASTM C1157 targets many of the same categories, but specific performance, right? So chemistries are not specified there. Still a hydraulic cement. And then, of course, ASTM C595 blended cements becoming very popular right now as well. Portland limestone cements, PLCs, which is a ASTM C595. It's a one-to-one replacement in performance for standard OPCs. It offers the same durability and resilience and offers a 2% reduction in the carbon footprint of the cement. An upcoming Concrete 101 webinar on June 2nd is going to go into greater detail regarding the types of cements and SCMs available to incorporate into your specifications. So I just wanted to briefly touch base on that. You can also get more information at www.greenercement.com, which is provided by the Portland Cement Association. So allowing those cements or Portland limestone cements are easy. They're already in the building code, and they're actually accepted nationally by ACI, the FHWA, the FAA, and also within the American Institute of Architects Master Spec. So they're very easy to incorporate into your existing specifications now if they're not there already. They're also accepted locally by IDOT, CDOT, and the Illinois Tollway. Some of them do require some performance testing to be done prior to for use in roadways or structures, but they are allowable. So again, very easy to incorporate them within your existing specifications currently. So fly ash, as you know, is a supplementary cementitious material. It's a byproduct from burning coal and power generating power plants. There's two types of fly ash, Class C and Class F. The advantages of using fly ash in concrete is they typically increase workability, they reduce permeability, they increase sulfate resistance or improve sulfate resistance of concretes, and offer improved ASR mitigation. I know in the Chicagoland area, which is where I work, there is certainly A lot of specifications that I read on a daily basis looking for ASR mitigation. So if you're limiting fly ash or not including fly ash within your specification, it may be challenging to provide adequate ASR mitigation. An easy way to do that is to allow fly ash in your specification. Typical amounts in concrete mixes for Class F fly ash are between 15 and 25%. And Class C are often used at dosages between 15 and 40%. And this is really for normal concrete. For mass concrete structures, we can see dosages even higher than those replacements. Slag, often called slag cement, ground granulated blast furnace slag is another supplementary cementitious material. It's a byproduct of the iron and steel making industry from the blast furnace operations. Typically 3 types, grades 80, 100, and 120. Again, advantages, it increases workability typically, reduces permeability, improves sulfate resistance and ASR mitigation again. Typical amounts in concrete mixes are a direct replacement for Portland cement of up to 95% in extreme cases, especially for higher strength concrete mixes at later ages, massive concrete structures. But 40 to 50%, even 25 to 50% is most commonly used. And then I'll turn this back to Gary for just a moment to talk about some e-ticketing, which is certainly something that is on the radar locally. Gary?
Yeah, e-ticketing, we suspect that e-ticketing was something that eventually was going to occur, but perhaps with the pandemic, it may have acted as a catalyst to push it forward even faster. It's being requested increasingly by the DOTs, obviously due to the safety factor for COVID-19. And currently, there are pilot programs being created to refine and implement the e-ticketing, which would include, trying to establish a uniform appearance to satisfy all the stakeholders involved. Along with the e-ticketing, you could provide electronic batch weights as well. Like previously with paper copies, you can provide those as well. And those would go out to those that are established at a pre-pour meeting on a distribution list to make sure all the stakeholders receive copies of it. Obviously, it eliminates paper copies and lost tickets. Yeah, it's not uncommon to get a lot of phone calls as a producer that they have missing ticket or batch weight copies, or that a batch weight wasn't received on a job site. We could also add relevant notes to the e-tickets as well, regarding inspection results at the plant and contacts for quality control at the plant. Again, we're still in pilot phases. I can't speak for anybody else. Internally, we are here, and we're still refining it. And then it's important to note that ASTM is finally removing the provision that mandates paper tickets. That doesn't mean that they won't be available upon request, because we'll still have the option to provide those as well. Because there may be some parties that may not have immediate access to email, and for that tiny segment, we would have to still provide paper copies of batch weights and the tickets as well. And Theron could actually expand on the, we do know that the IRMCA has been heavily involved in bringing this whole process to fruition, and we'll turn it back over to Theron.
Thanks, Gary. Scott, Gary, great job presenting today. And to further talk about e-ticketing, it's one of those new technologies that producers are grabbing onto. It just saves so much time in finding, like you said, paper, filing it, storing it, uploading it, sending it to somebody. The e-ticketing movement is moving fast in Illinois. Jim Randolph, the executive director of IRMCA, has worked hand in hand with IDOT in some pilot projects to get IDOT trying it, testing it, and creating some policies for it. The Tollway has worked with IRMCA in industry to write an actual e-ticketing policy. So they're have some pilot projects going forward this year where they'll test out the policy, work out the kinks, and move forward with it. And as you heard today, there's a lot of different technologies that are out there that you may not have in your specs. We're hoping that you feel more comfortable with them, and they're things you want to add. And I think e-ticketing is just one of those things. It's something where the concrete industry is looking for the engineering community to put some provisions in their specifications to allow for e-ticketing on projects. And if that's something you'd like to do, the Illinois Ready Mix Concrete Association would be glad to put a working group together with engineering firms to discuss what the language should be regarding e-ticketing and making sure you're comfortable with it and working with it. Scott, if you go to the last slide. In our closing comments, we find a lot throughout the state that engineers specify the same type of concrete 100 different ways. Sometimes all the ways aren't correct. So the Illinois Ready Mix Concrete Association would be interested in putting together an engineering working committee to standardize concrete specifications for the state of Illinois. So if you've got a project in Illinois and you're going to specify 4,000 PSI concrete for an exterior pavement, we would all work and have similar language. Sometimes specifications limit a concrete producer to use technologies that would actually make the concrete perform better, last longer, and it doesn't mean that there's additional costs involved. So if you would be interested in having one or two people from your company work with IRMCA and other engineers throughout the state to kind of create a master concrete specification where we would talk about things like fly ash and slag and ternary mixes, binary mixes, things like Portland limestone cement, adding that to your specifications. You could just shoot an email to Theron Tobalski, ttobalski@irmca.org, and we can organize a committee with that. Our next webinar is on June 2nd at 12 p.m. It's called Concrete 101, the Basics of Concrete. I'll be presenting during that webinar. We're going to cover a lot of the things that you heard today and much more in depth, and then we're going to cover some other topics that you did not hear about today. So it's a great webinar for you if you're writing concrete specifications or if you oversee concrete on a project. Registration will open on Monday, May 24th. As mentioned in all the other webinars, we offer free engineering assistance. And definitely what we've noticed is some of the engineers who are turning into these webinars, as questions come up, they've been really great about contacting IRMCA and saying, hey, I need help with this. How do you do this? How do you specify that? So we appreciate you reaching out to us and want you to know that we're a free resource for you. Again, we are on LinkedIn. We're advertising these webinars. We're sharing technical information. So if you're not following the Illinois Ready Mix Concrete Association, please look us up and start following us. And then we also are on Facebook and Instagram. We highlight a lot of our members and we highlight a lot of their technologies. So thanks again for tuning in today and hope you have a wonderful day. Thanks.